Hi, everyone. It's 2 p.m. Eastern Time. Um, uh, so we're going to start now our webinar on what counts as physics. This talk was part of a session that we did at the APS 2024 March meeting in Minneapolis. I'm Alberto Martinez. I'm past chair of the Forum on History and Philosophy of Physics of the American Physical Society. The session that happened at the March meeting was organized by Professor Joe Martin, and it had several speakers, including Andrew Zangwill here present, Sarah Bridger, and Francis Hellman. Today, our speaker is Andy Zangwill. He is very well known as the author of the successful book Modern Electrodynamics, published by Cambridge University Press in 2012. He's also the author of two other books, including A Mind Over Matter, Philip Anderson and the Physics of the Very Many. His talk today is titled That's Not Physics. It's going to last approximately an hour. While he's talking, any of you are welcome to please write comments on the chat. And when he's done, we'll happily turn over to some sort of a discussion based on your comments. So without further ado, here's Professor Andy Zangwill of Georgia Tech. That's Not Physics. Welcome, Andy.
Thank you, Alberto. It's a pleasure to be able to do this, and welcome everybody who's tuned in. And of course, the idea of the title is a hook to say, well, what in the world is that supposed to be about? And so let me tell you right away where this title comes from. So, for example, here's a quote from Werner Heisenberg. One day, Max Born, he was in the group of Max Born, discussed a theorem which implied that non-periodic electron orbits were possible. Enrico Fermi, who was visiting our group, immediately declared, "That's not physics." Robert Wilson, who was the first director of Fermilab, is talking about his life, and he says, "My thesis was about the theory of the cyclotron. But to me, that's not physics, so I started banging protons together." So he didn't regard theory as physics, but experiment was. Bob Park, who for many years was the director of public information for APS, in a memoir says, "A group of us asked the American Physical Society to devote an invited session to surface physics at the next March meeting. It didn't happen because we were told that's not physics." So these sorts of statements got me thinking about this idea of, well, what are the boundaries of physics? Is there sort of a fence, and the physics is on the inside, and what's not physics is on the outside? And of course, physicists think they can do anything anyway. And so what exactly is going on here? And so that's what I'll be talking about today. So roughly speaking, outline of the talk. Well, to know what is not physics, we need to start out with what is physics. So we'll say a little bit about that, get into the not physics, and I'll actually give you 3 case histories, which are quite different and indicate sort of what the history of this entire idea is, going back really to the foundations of the American physics community, which is to say the American Physical Society. So, okay, so what is physics? Well, I guess whatever is in these freshman textbooks is supposed to be physics. And so here's an example. Many of us like to do a laboratory demonstration of this sort of thing. So probably we would all agree that, banging these things together is physics indeed. But, let's turn to dictionaries. That's always nice to know. What are definitions? Let's start with, Daniel Webster, right? Early dictionary. Physics, under the physics, it says, pertaining to all material things, obeying the laws of nature, as opposed to things mental, moral, spiritual, and imaginary. I like the imaginary part. Move forward, many folks would say physics is what physicists do. And if you try to track this down, at least the earliest reference I can find is 1938. Physics is the activity of a physicist. And that's Bruce Lindsay, who for many years was the chairman of the physics department at Brown University, and also actually a philosopher, and wrote some serious philosophy as well. But for the purpose of this talk, what do I mean by physics? I mean the research specialties of the faculty members who are hired and retained by American physics departments to teach, publish, and train PhD students. Now, of course, those PhD students go out and get all sorts of jobs in all sorts of places, but because their training and how they think about being a physicist typically is formed when they're in graduate school, and then their advisors are the ones presumably who injected that into them, then I think this is not an unreasonable definition of trying to decide what physics is at any particular moment in time. So that's the definition that I will be using. Okay, now, if that's physics, then what is not physics? Well, here's an example. Again, we would all agree, second law says we can't have spontaneous flow of heat from cold to hot. So I think we can all agree that's physics. Or not physics, I should say. But it turns out that lots of other things turn out to be not physics as well, including things that maybe you thought were physics. The first person, turns out, who actually defined not physics, you can go all the way back to the founding of the American Physical Society. And here's the first president of the APS, Henry Augustus Rowland. It's a famous portrait by Thomas Eakins of Rowland on the right. And he gave a rather famous address as the president, which was called The Highest Aim of the Physicist. So you can see the date there, 1899. He's the first president. So if you didn't know, you now know. And Alberto said it's the 125th anniversary. So we know how old the organization is. So here is part of what he wrote. He said, and then it was published, "Let us cultivate the dignity of our pursuit. This will sustain us in a world which gives its highest praise not to the investigation of pure physics, but to practical physics, which ministers to physical needs rather than to intellectual needs." So what was he talking about? What is pure physics and practical physics? Well, practical physics is, well, what we today would call applied physics. What he was talking about was the application of physics to all sorts of different things, which, God forbid, might have practical value. And, he was concerned that we live in this world for example, he's talking about people like Edison and such folks who were lionized by the public, and he didn't want anybody to think that, Edison was a physicist or anything like that. And so this was the very strong message that he was trying to convey. And that message is one of elitism. I mean, that's pure and simple. That's what it is. And that elitism has consequences. So, for example, Lloyd Jones, and that's the correct spelling of his first name, he was, in fact, his title was chief physicist of Eastman Kodak in the early part of the 20th century. And in his memoirs, he writes, "I read a paper about applied optics at a meeting of the APS, and not a soul was interested." Similar from Harvey Fletcher, who was the director of physical research at Bell Telephone Laboratories. He also, by the way, was the student who actually did the oil drop experiment in Millikan's lab. He's the one who did it, but Millikan wrote the paper and didn't put Fletcher's name on it. But that's a different story for a different day. In any event, Fletcher was a very well-known guy. And he, of course, at Bell Labs was interested in acoustics. And he writes there, we in acoustics were frustrated. No one listened when we presented papers at APS meetings. So you get the idea. The folks who were trained at PhDs in physics went into industry, optics, acoustics, whatever. They didn't feel when they went to meetings of the APS that anybody cared. And this got to be a problem. And so what did the APS do? Well, what does any group do? They make a committee. They made a special committee on applied physics. And that committee reported out in December of 1930. And this is actually the first paragraph in their report. "Many physicists are dissatisfied because they feel that the APS is overly concerned with quantum physics and doesn't represent physics as a whole. This feeling is quite general. And whether justified or not, it's led to an optical society," that was in 1916, "an acoustical society in 1929, and a rheological society in 1929. And so this was a big worry. What they were worried about is that APS members would start leaving the American Physical Society and just being members of these sort of specialty societies. And they were concerned that the entire society would wither and die, essentially that it would balkanize. And that was a big problem. So they were trying to figure out what to do about that. These societies were already being formed. The solution was the creation in 1931 of the American Institute of Physics. Some of you may, what is the AIP? Am I a member of the AIP? Well, what that was essentially an umbrella, and is an umbrella organization, sort of a big tent, so that everybody, no matter where you were working in the physics world, you felt you were part of the same, the same organization in some sense. So it's actually has these member societies, and the original member societies in 1931, the APS, the Optical, Acoustic, and Rheology Societies, and another society that had been formed just a few months earlier, the American Association of Physics Teachers. Why was that formed? They had the same feeling. They would go to APS meetings, they would talk about pedagogical issues, and nobody would show up. And so they were unhappy about that and formed their own society. And so this was an attempt by sort of the American physics leadership to keep the physics world from fragmenting. So the AIP, took it upon themselves to start doing things to try to, educate different parts of the physics world about each other. So one thing they did fairly early on was to have a huge conference called Physics and Industry. That was in 1936. And they brought in all trained physicists who are working in different industries. And each one of them spoke and then wrote a paper, which was published later. And one of them, which I particularly like, is this one. It's called Let the Physicists Change Your Oil. And that was given by Paul Foote. So he was director of research at Gulf Oil, but also, as you can see there, he was the APS president in 1933. And so there are quite a large number of industrial physicists who were deeply involved in the APS in the early years. And that's part of the reason that they were so concerned that industrial folks were sort of being ignored. And in this paper, he says, I present here some perplexing problems arising in the lubrication of automobile bearings. This paper was published. You can read it in the Journal of Applied Physics. It is a wonderful, beautiful paper using really beautiful physics concepts in order to understand a whole range of things which are associated with lubrication. And any one of us, believe me, would be proud to publish this thing. I urge you to look him up, Paul Foote, and find this paper from 1936. It's actually published in 1937, I believe. So they were trying in order to, keep everybody happy. Now, the APS, that's the AIP, the APS responds similarly to these concerns because in 1941, RCA marketed the first commercial translucent electron microscope. There it is on the right. And almost immediately, 3 PhD physicists found another society, the Electron Microscopy Society of America. This is a disaster. And not only that, they went to the leadership of the APS and told them that they were doing it. How did the APS respond? They panicked. And so they created the first divisions. What was the first one? Oh, guess what? It was the electron and ion optics division in order to hold in the people who might have bolted for the Electron Microscopy Society. Well, then we get the polymer physics division. That's the second division which ever gets formed. And so you can see, again, the idea here is to provide a home for these people that Rowland had essentially demonized, not demonized exactly, but marginalized, let's say, by saying that the practical physics that they did, wasn't on the same plane as the pure physics that he felt that the APS was supposed to defend. Well, there's this fear of applied physics, and it's rampant. And you hear, for example, Frederick Seitz, who was the president of the National Academy of Sciences and also of Rockefeller University. Some of you may recognize the name Seitz. He's the author of the first textbook of solid-state physics, for example. And talking about other possible divisions which might get formed, he says, those who oppose the creation of divisions are concerned. And so much emphasis will be placed on applied physics that the society could be inhibited from handling its duties toward fundamental physics. So again, this notion, the APS is about fundamental physics, and these other things, we can't let them take over. It really is funny because it was a misplaced fear. Because if you look at the APS membership as a function of time here from near the beginning of its formation, as time goes on, and you can see the various members, perhaps you work in industry, you work in government, the so-called 20 leading schools, that was as if the US news people had been around in those days. You can sort of imagine which of the universities they were, and other education is all the other colleges and such places. And that peak you see in this industry around 1920, where their membership, they constitute about 25% or maybe 23 or 4% of the total APS. That is the all-time high. And so even though Zeitz is writing in 1945 and he's worried about some takeover, in fact, the proportion of folks who work in industry who are members of the APS just declines and declines and declines. And it never even has come close to approaching the number that it was at in 1920. And so the APS, has been attempting to deal with this for their entire history. We fast forward all the way to 1975. There's a survey of applied physicists, and the main response is that many academics disparage working in industry. So what does that do? What does the APS respond? They create a committee on applications of physics. Fast forward 20 more years, another survey of applied physicists. What comes back? The APS doesn't serve our needs. What does the APS do? They've done a committee. So now they have to create a forum. And this one's on industrial and applied physics. They actually publish a magazine for a few years until they run out of advertising money. And even as recently as 2019, if you look at the strategic plan, did you know the APS had a strategic plan? They do, and they were going to offer special benefits to encourage industrial physicists to join. I haven't circled back with the APS to see how that worked out, but I think what you can see is that there's been a problem all along of this sort of first and second class status of whatever pure physics is supposed to be and whatever applied physics is supposed to be. But at least in some people's minds, if it is physics, it's only barely so, and it's certainly some second class type. Okay, so that's how sort of the idea of not physics gets born. It actually gets born at exactly the same time that the American Physical Society gets born. Okay, so I now would like to turn to 3 case histories and show you different ways in which the not physics idea has cropped up. I'll talk about acoustics, I'll talk about cosmology, and I'll talk about biophysics. So these are 3 areas that have had different trajectories over the last century in the relationship of what's going on in these fields to, well, what we would like to call physics. So let's get started. I'll start with acoustics. Now, so acoustics was physics once. Now, what do I mean by that? Of course, acoustics is physics in the sense that you can open a freshman textbook in physics, and there's very likely to be a discussion of acoustics and waves and pipes and open-ended and closed-ended and all this. So nobody doubts that it's physics in that sense. What I mean, if I go back to my definition at the beginning of this talk, is can you go to graduate school, say, in a physics department and get a PhD doing a research problem in acoustics? All right. Now, the answer to that is yes, that was the case at one time. So one of the principal texts of acoustics is shown there on the left. It's the Theory of Sound, written by Lord Rayleigh, shown there on the right, in 1877. And a lot of people thought that that book sort of closed the door on research in acoustics, that Rayleigh had said it all, and there was nothing left to do. But in fact, Rayleigh, who lived quite a bit longer, as you can see, continued to write research papers on acoustics, and in fact, up until the year of his death, he continued to do that. So for him, it was not a closed subject. It continued to be a research topic. And in fact, if you look at, say, I just picked sort of a random one early in the century, the 20th century, 1920, the annual meeting of the APS is kind of quaint. There were 125 attendees, and there were 34 contributed talks. And if I show you the titles to some of these talks, in 1920, these are things that you might expect, right? Recoil of alpha particles from light atoms, pulling electrons from metals using strong electric fields, okay? X-ray spectrum of platinum. You go to the bottom, electromagnetic induction and relative motion, that's special relativity. So these are all things which sort of make sense, you would expect, but you might not expect these, which were also some of the contributed talks: the pitch of organ pipes, sound pulses through curved tubes, a proposed standard for sound, right? And so there were only a total of 34 talks at the entire meeting, right? And so 6 of them are on acoustics. So, and this is research work, which is being reported at the APS. So there's absolutely no doubt that this is a research topic which is taking place all across the country. So for example, just a few years later, this is a physics professor at Harvard, George Pierce, who is reporting in the Physical Review sound velocity measurements at ultrasonic frequencies. And what's kind of interesting about this paper is the vacuum tube amplifier. This is when vacuum tubes are starting to be applied for various experimental measurements. And so Pierce was reporting on results for measurements of sound in ultrasound. So again, a research topic without question. World War II provided an enormous boost for acoustics research. So here, for example, a sonar image of a Soviet minesweeper in 1941. And the Navy, as you might imagine, wanted a lot of research. They scooped up physicists and got them working. And by the end of the war, they were able to publish 22 volumes. It's called the Red Book. It's actually many books. And just one of those volumes I show here, The Physics of Sound in the Sea. And if you look at the author list in here, these are all people, many who went on to do various other things in other fields. But they published this thing as these various things that they did during the war as research papers later on. And in fact, the center for much of this research was at Harvard. On the right-hand side, there's a picture of the Harvard Underwater Sound Laboratory. You see when it was in existence. And on the left, I'm showing 5 folks, each of whom were a full professor of physics at Harvard. The year is when they actually started working at Harvard. And there's George Pierce. You see him, the third one. The director of this laboratory at Harvard was the next person on the list, Frederick Hunt. And you can see the various types of things that they did: architectural acoustics, musical acoustics, ultrasonics. And in fact, during the time period, in the first half of the 20th century, 14 people got PhDs in physics for topics in pure acoustics. So again, no doubt that acoustics was physics in the sense that I've defined it. However, acoustics sort of abruptly became not physics at Harvard in 1946. And that's because all the teaching and all of the research in that subject moved out of the physics department and into a newly created department, and today it's a college at Harvard, called Engineering Sciences and Applied Physics. And so after that date, there were no more PhDs in physics, in acoustics at Harvard anymore. They were all PhDs in applied physics. So Harvard made the decision, sort of a conscious decision, to eject acoustics as a physics subject and turn it into an applied physics subject. Here's another example. Just pick another place. This is Texas, the physics department at Texas. So in 1930, they hired a gentleman named Paul Bohner, whose specialty was acoustics. And in fact, he was really interested in organs. And so on the right-hand side, there's a picture of Bohner, and it says there, the physics department pipe organ. That's because as a research topic, he and his PhD students built this organ. It had 1,600 pipes. And he, in fact, played it and it went out on the radio on Sundays for church music from the basement of the physics department at the University of Texas. In fact, Bohner was recruited into that underwater sound laboratory at Harvard. And after the war, he went back to Texas and he took 3 people with him. There they are listed on the left. And they were all acousticians. And they did acoustics research at Texas for many years, doing that underwater work, seismic work, physical acoustics. They produced 20 PhDs in that time interval, all in physics. But Texas, like Harvard, decided that at a certain point, acoustics was no longer physics, it got moved out of physics, and in the case of Texas, as is more typical all around the country, into electrical and mechanical engineering, and it was no longer possible to do a research problem in the physics department and get a PhD. So, and this gets played out all across the country, where folks who are doing research in acoustics, they retire, but they're not replaced, or they're moved into other departments. You can see this sort of writ large in 1964. The government asked the physics community, actually the National Academy of Sciences and the National Research Council, asked the physics community to look at itself and describe itself to the government for no other reason to help them with funding decisions. And so it's a document that looks over all of physics. It's named after the chairman of the committee that did all this work, George Pake. And here's what they have to say about acoustics. Work in acoustics has received stimulation from its engineering applications for loudspeakers and microphones, full stop. You know, it's not a ringing endorsement as acoustics as a research topic in physics. And in fact, it begins to atrophy over time, and the education sort of disappears from physics departments. Here's a conference on education and acoustics, which is held, sponsored by the American Institute of Physics in that same year, 64. And the keynote was given by a professor of mechanical engineering at Cornell. And he writes, the fundamental interest of the physicist is to understand nature. In acoustics, this understanding is required by engineers to alter the environment for applications. That's why research and teaching in acoustics have passed from physics to engineering. And in fact, that's exactly what happened. If you ask about acoustics as a research specialty in US physics departments, you can actually track this because for many years, the AIP published this wonderful book called Doctoral Programs in Physics or Graduate Programs. And it actually lists every single PhD physics program in the United States, their faculty, what they do, the amount of money that came in, PhD students, and incredible documents. So you can actually track exactly what's happened over time. And what you discover is that, you know, in the decade of, say, the 50s, 20% of all US physics departments had a professor or professors who were doing acoustics and having PhD students. And by you get to the next 15 years, it's down to 10%. 1980 to 2000, it's down to 5%. Okay, 21st century, 1%. And at this moment, there are 2 PhD programs in the United States, physics departments, which have a group doing acoustics. One is the University of Mississippi. The other one is Brigham Young University. So you can sort of see that from having absolutely been physics at the beginning of the 20th century, by the end of it, acoustics was no longer physics. All right, let's go the other way. Let's start with something that was not physics and turned into physics. Cosmology was definitely not physics at one time. Here's a time when it wasn't. In the middle of the 19th century, Edgar Allan Poe could actually give a public lecture whose title is On the Cosmogony of the Universe. In case you're not familiar, cosmogony it means the birth of the universe. And he gave a long public lecture and later wrote a long article about this. It is 100% speculation, of course. If you read it, it's quite amazing because it really sounds a whole lot like the Big Bang, to be truthful. But nevertheless, it wasn't physics. It was just an invention of his mind, you know, sort of like, well, the Raven and things of that sort. The birth of real scientific cosmology, of course, was in 1917 with Albert Einstein. This is actually a portrait of him, a painting which was made in that year, 1917. The paper was called Cosmological Considerations in the General Theory of Relativity, which he wrote not because he was so interested in the universe per se, but he wanted to test his theory and see if it made any sense. And he felt that it did, with various caveats about the cosmological constant, which we won't get into here. But the question I want to ask is, how is this taken up, particularly in the United States? And really, you know, the only, let's say, data which was relevant to cosmological issues through the 20s was not collected by a physicist per se. It was by an astronomer, Edwin Hubble, This is his famous data, which is showing the radial velocity of extragalactic nuclei as a function of distance, which at the time it wasn't immediately understood what that meant, and was eventually understood in terms of the expansion of the universe. But it really attracted attention of astronomers. But in physics departments, again, I'm not talking about astronomy departments, say, I'm talking about physics departments. There were only two places in the 1930s where there was anybody on a physics staff anywhere in the United States who was willing to take cosmology, looking at the whole universe as a physics problem, seriously, right? East Coast and West Coast. At Caltech, Richard Tolman, in 1932, he writes, cosmology is a dangerous term with a long background of dubious metaphysical association. See Edgar Allan Poe. On the other coast, at Princeton, Robertson is writing, the version of Einstein's general theory to apply to cosmology is made in part using hypotheses that appeal to one's philosophical predilections. I challenge anyone who go to a PhD defense, and if the student says that what they're doing is based in part on their philosophical predilection, the hypotheses they choose, they're likely not to get out of the room with a PhD. So it was perfectly clear to both of these folks that they're dealing with a subject which is not on the type of foundation, let's say empirical foundation, that the rest of physics is. And that was simply the case, right? You can really see that if you read a Scientific American article by Freeman Dyson in 1958. It's actually a survey of all of physics. And it has exactly one sentence about cosmology. And that sentence is this one: to most physicists, cosmology is not a respectable subject to think about. So this is 1958. Stephen Weinberg, writing much later in the first 3 minutes, is musing back to when he was a graduate student, which was the late 1950s. And he says the early universe was not something to which a respectable scientist would devote his time. So the punchline here is that, unlike acoustics, which was definitely a physics topic in the beginning of the 20th century, cosmology was definitely not a physics topic at the beginning of the 20th century. It's interesting that both Weinberg and Freeman and Dyson use the word respectable, or I should say not respectable, in connection with this particular subject. So what happens? Well, this is what happens. It goes from a subject with no empiricism to a subject with empiricism, the famous discovery of the cosmic microwave radiation in 1965 by Wilson and Penzias. And just as sort of an illustration or an underline to how much this was not physics, they were completely unaware that 20 years earlier, George Gamow had suggested this idea, what we today call the Big Bang, and with his earliest collaborators, Alpha and Herman, had actually predicted the cosmic microwave radiation at exactly the effective temperature that they saw, but they didn't know about it at all. So nevertheless, once it was understood that this was something that you could actually do measurements on rather than merely speculate, then things begin to take off. If you look in the United States in the 60s and 70s, the Big Bang scenario begins to gain adherence. Willie Fowler out of Caltech leads in detailed nucleosynthesis calculations. There are observed cosmic abundances of helium-4, which one can compare with, and it begins to get some traction. But I would say the really big thing was that particle physics physicists realized that the hot early universe, which was one of the things that Gamow was pointing out, was a laboratory for high energy physics at extremely high energies, which is to say high temperature. And at this time, rather exotic theories were being proposed, but they've only got interesting at very, very high energy. And so the early universe was a place to look. And so there was a way to, in principle, test new ideas in particle theory. And the late David Schramm was really a leader in trying to interest particle physicists in cosmology, which, as we saw, Weinberg, he was taught that this was a subject you should stay away from. Nevertheless, by the 1980s, many particle physicists had become sort of part-time cosmologists. And sort of the evidence that this was real is that Leon Lederman, who was the second director of Fermilab after Robert Wilson, who we met earlier, he created a group at Fermilab in theoretical astrophysics. And that really sort of normalized that whole subject. That wasn't going on amongst particle physics groups at universities. So he started this one at Fermilab, and as I say, normalized it. That's on the theory side. On the experiment side, through the 80s, John Mather and collaborators were putting together the COBE satellite mission, and which famously established, without a doubt, that the cosmic radiation background that had been discovered by Penzias and Wilson was actually a black body character. And so it was all becoming very, very real with the interplay between theory and experiment. And so you see, if you look across the entire United States at in physics departments again, who is doing cosmology? In 1964, there are only 6 schools doing it, and the red sort of is what you might call, I don't know, top 25 or something like that schools. So they're sort of the highly ranked places have one person at each of these places doing cosmology in 1964. You jump to 1980, and this is the universe of American universities who are doing graduate work in cosmology. And now the parentheses are the number of people. And so at Caltech, they've now gone to 3 people. Chicago has, say, 2, et cetera. And you can see there's a lot of red in here. And so what that's meaning is that the so-called top schools have embraced cosmology without any question. And by the time you get to 2000, there's no doubt that cosmology is physics. In fact, it's hard to find a physics department that doesn't have somebody who says they're a cosmologist. And here I've just sort of indicated at this particular moment in time where were the biggest groups. This is not by any stretch all of the places, but you can see you're having large fractions of physics departments devoted to cosmology at places like Hopkins and Caltech and such places. So this is a success story for cosmology, moving, from something which was philosophy at best and voodoo at worst, to firmly a part of being in the physics firmament. And why? Because of the ability to do measurements and compare to theory and move forward as one happens in other fields. Okay, my last example is going to be biophysics. So this is an interesting topic because it's sort of the collision of 2 very large areas, right? Physics is, of course, a large area on its own, and biology is an even larger, if you like, area. And so this is some kind of a place, the borderline between them. And you can see how disparate something called biophysics is by simply looking at the title of some books that are published on this. So we start in the upper left, single molecule biophysics. You go to the right, there's the biophysics of DNA and mitochondria. Then there's the whole field of radiation biophysics. What is the effect, of X-rays and radioactive particles and such things on living things? Biophysics of insect flight, right? Lower left, molecular and cellular biophysics, muscle biophysics, membranes, and on the right, far right, mathematical biophysics, right? So you have all of this stuff, and it's entirely possible, and if it is the case, if you go to at least biophysics departments around the country, you can find entire departments which have the research that they do has no relationship whatsoever to the research done at some other biophysics department somewhere else in the country. Many of which, by the way, some are in academic, some are at universities, some are in medical schools. So biophysics itself, it's hard to say what that is, because the people who say they do that are all over the place in both medical schools and academic institutions and in other subs. So I'm not going to even try to do that. I'll be talking about biological physics, by which I mean people working in physics departments, if you like, professors of physics whose research touches on living things, all right? And so that's a tiny fraction of all of biophysics, but already it turns out to be a complicated story, which I'll try to give you the history. Interestingly, it starts pretty nearly at the beginning with our friends up at Harvard. They actually made a purposeful hire in 1920 of an assistant professor for the express purpose of working in this area. His name is William Bovey. And you can tell that's what was going on because, you know, he was teaching classes both at the undergraduate level and at the graduate level, biological physics, it was his title, by the way, back in 1920, biological physics of the sense organs, special topics, that was for graduate work. And then he published papers on his work, electrical response of the retina, physiological effects of radiation, biophysics of ultraviolet. These are all topics which make perfect sense for a physicist to work on at that period of time. So it looks like things are off to a nice start in this field as early as the 20s. But if you look at the dates, the date at the very top where I have him as an assistant professor of physics, those are the dates when he was at Harvard and working. And so it's 5-6 years. And if you have any connection with academia, you sort of know what it means when someone is at a place for 5 or 6 years. And we can all say it at once, he didn't get tenure. That's right. He did not get tenure. He was booted. Now, he went on to found a biophysics department at Northwestern University and subsequently had a very interesting history. But at least as being in the physics department at Harvard, no way. And in fact, you can then ask the question, when is the next time that Harvard University hired an assistant professor for the purpose of doing biological physics? And the answer is it took them 90 years. 90 years to hire another assistant professor working in this area. So, in fact, that story alone gives you some indication that what might or might not be going on with biological physics in physics departments in the United States. Now, you remember the big tent of the American Institute of Physics and that early symposium in 1936 on industrial physics. Well, a year later, they mounted another very large symposium on biophysics. And the organizer for that, this picture there is on the left, was Detlev Bronk, who is an absolutely fascinating person and was a powerhouse in the American scientific community. He was the leader of the Johnson Foundation for Medical Physics at the University of Pennsylvania, actually was the first director. He became the president of Johns Hopkins University, the president of Rockefeller University, just a very important fellow. He gave the keynote speech, which was called The Relation of Physics to the Biological Sciences. And what he says is quite interesting. This is 1937. I've had little difficulty persuading physics department chairmen at our larger universities that it's desirable to appoint biophysicists, but its accomplishment is blocked because the same appropriation, money, brings a spectroscopist, a nuclear physicist, interestingly, or a cosmologist, all of whom bring the department more glory among physicists. So in other words, yeah, they're willing to hire a biophysics person, but not if there's a spectroscopist or a nuclear physicist or a cosmologist on the market. So, all right, there's already an issue going on here in 1937. Now, what's interesting about this particular topic is that it's sort of like a siren song to many physicists. So, for example, Niels Bohr, as early as 1933, wrote an article in Nature called Light and Life, where he speculated about quantum processes associated with vision, for example. And that talk famously motivated Max Delbruck, who some of you may know as one of the founders of molecular biology. He was trained as a physicist, but this talk that he heard converted him to that new subject. Perhaps even more famously, in the middle of World War II, Erwin Schrödinger wrote this little book called What is Life, where he talks about, can we, as he says, rationalize biological phenomena with the laws of physics as we understand them. And he talks about some genetics things in here. It turns out that the details of what Schrödinger had to say were not particularly right, but he said, and he motivated a large number of people, basically through his status, that, you know something, biology is a subject that physicists should take seriously. And you can ask the why questions, just like we do everywhere else in physics. You can ask them about biological processes, which was not typically how biologists were approaching the subject at the time. They weren't asking the sort of why questions so much. On the right, again, just sort of for fun, this is George Gamow. That's the fellow who proposed the Big Bang theory. He got interested in biology, and in '53, he actually wrote this book, sort of a book for kids, about learning the facts of life, but it's from a physics point of view. And in fact, Gamow, who was at George Washington University, when he took the job there, he asked him to sponsor a conference every year on theoretical physics every year, which they did. And in '46, you see here, which is the same year he proposed the Big Bang, by the way, his conference, he decided to organize it on the subject of the physics of living matter. And Gamow, who was well known for other things like describing alpha decay of a nucleus by tunneling, he's very well known. He invited his friends. And who were his friends? Well, Niels Bohr, Leo Szilard, Edward Teller, John von Neumann, all these famous people, they came to his conferences. Now, what did any of them know about living matter? And the answer is nothing. And so Gamow had the foresight to also invite people, physiologists, who would explain what were the interesting problems to these folks. And just to show you what a brilliant fellow Gamow was, 4 of the people he invited to this conference later went on to win Nobel Prizes in physiology. Now, did any of these people become converted to biological physics? No. Leo Szilard, of all of them, was the only one who did a little bit, but it's hard to say that he did anything of any significance. So this kind of died. But it just illustrates, again, this sort of honey-like attraction. Can we maybe do something here? Well, maybe yes, maybe no. Here are 2 folks who really did. So you have to go a little more forward in time. Both of these folks made careers in a more conventional area of physics. And then at the age of 40, they both independently decided to get into bio. So on the left is Hans Frauenfelder, who was quite well known as a nuclear physicist, experimental nuclear physicist, who in 1960 essentially gave it all up, and at the beginning through Mossbauer spectroscopy and later through other things, started studying, in his case, molecules. So as he says, to a physicist, the structure of a biomolecule determines its energy landscape, and it's that landscape which determines its dynamics. It's a very physicsy type point of view. In fact, even though I write biophysics there, Frauenfelder himself hated the word biophysics. He always talked about the physics of biomolecules. That was his language. Now on the right, and this slide, I promise you I made this long before the recent Nobel Prize announcement, that there's John Hopfield, who again had a successful career as a theoretical solid-state physicist at Bell Labs and at Princeton. And in 1970, he switched to bio. And as he put it, my solid-state physics training led me to think about biological networks rather than individual molecules. And both of these gentlemen had a significant effect on younger people because they were both successful already in other areas and decided that this was a fruitful area to get into. Now, remember that Paik report, which was the 1964 National Academy discussion of all of physics. Turns out these are called decadal reports because they come along once every 10 years or so. You have to convince people to sit on this committee and someone to chair it. In this case, it was Alan Bromley, nuclear physicist at Yale, again, sanctioned by the National Academy, the NRC. This is an enormous report compared to the Paik report. They have a subpanel on what they call biology in physics. Already the name is interesting. And here's what they write. Physics departments have rarely tenured young people working in biophysics. It's been difficult to evaluate their work, and questions arise about the appropriateness of their work in a physics department. So this is 1972, and you can see that this attitude that there's something, is this physics or is this something else? And they just remarked it's been difficult for folks who to get tenure, at least at that period of time. So here's some numbers. So this is the number of physics departments which have n people on their staff doing biological physics. All right. So let's look at the red first, because that's 1964. And you can see, well, the largest, there's one person at, say, 30 physics departments out of 136 total PhD programs. And there's one person. And in almost every case, that one person had made a career in something else. And at a certain period, they switched to biological physics, and they already had tenure. So there was nothing that their department could do about them. So that's n equal to 1. And then the number of departments who are willing to go up higher than 1 is minuscule, right? There's 2, 3, and 4, and there's less than 10 total. So the number of folks doing this is very tiny. You jump all the way to 2000, where the number of physics departments has gone from 136 to 231. And now you look at the blue, and you can still see that by far the largest 50 departments or so have exactly one person who's doing this kind of work. You're now up to, say, 30 that have a group of size 2. But interestingly, there are a small number of institutions that decide to invest in this area. 6 and 7, groups of size 6 and 7. Where are they? In case you're interested, right? San Diego at that time had 6. They have more now. And University of Illinois, which is where Frauenfelder was, and Northeastern, which is interesting, have these rather large groups. But really, they are the outliers. They're the anomalous departments with a group of that size in the year 2000. Here's another sort of interesting graph. This is raw data. So it's showing at all these different years between 1910 up to 2020, in that particular year, how many physics professors got into biological physics. In other words, they were hired to do this, or they switched in that year into biological physics. And the orange are the number of people who leave. So that is to say, they were doing biological physics and they got out, or they retired, or they died. So that's how you get on the orange graph. And what's interesting, of course, is the difference between these two. And there's sort of 3 sort of peaks here where you get a net increase in the number of people in the United States in physics departments doing biological physics. And one of them is the post-Sputnik area, like 65 to 75. That's that one sort of peak. There's a smaller one earlier, right after the war, which I can talk about if anyone's interested, World War II, if anyone's interested. But the really dramatic one, you see, starts at around the year 2000 and lasts for about 15 years, where you get a large increase in the number of people who get into biological physics in the United States. And you can see the same thing in other types of data, like in the number of PhDs and various things. There's a sort of a rather abrupt jump, which happens after the year 2000, after really not a great deal happening in the subsequent, 100 years. So you can ask, what happened? And here's a speculation, which I will call the Stephen Chu effect. Stephen Chu is an atomic physicist, and in 1997, he won a Nobel Prize for cooling and trapping atoms. Now, what happens when you win the Nobel Prize? Every physics department invites you to give a colloquium, and you come and you talk about the work that you did. That's all fine, and he did that. But it turns out that in 1997, Chu switched fields. He got out of atomic physics, and he started trapping molecules of DNA, for example, and doing what we would today call single molecule biological physics. And so the talks that he went around and gave, first 45 minutes, and he confirms this, were about atomic physics, but he always ended by saying, here's what I'm doing now. And so he was talking about biophysics in all these places. And by speaking with people who were chairs of physics departments at that time, at least in a fair number of cases, Chu normalized the subject for folks who may have been suspicious of it. If Stephen Chu, who got a Nobel Prize in atomic physics, finds this interesting and physics worthy, then maybe it is. He went to his monitors at the NSF and said, hey, I'm getting into a new field, but the NSF physics division doesn't fund biological physics. Can't you establish a program? And he actually helps, or he's actually convinces Denise Caldwell, who's in charge at that time, And she starts a program called the Physics of Living Systems. She brings Chu in to lecture to the NSF, to the people who are working there, and that program continues to this day. And if you look today, 2024, at, say, the US News rankings and such things, you'll discover that at most of the top physics departments today, there tend to be greater than 3 bio-engaged professors. But what's interesting is that not all of them. And if you look at maybe the top 20, there's 3 or 4 where there's 0 or 1. And that's interesting. And one can ask oneself, why is it the case that there are major physics departments around the United States that at this moment have exactly nobody working in this area? So the status of biophysics, biological physics, it's definitely on the road to normalization. Maybe it requires a few more deaths and retirements before it finally appears everywhere. But it's an interesting story, quite bumpy and different than a field that started and left and the reverse. Well, I could talk about all kinds of other subfields. Every one of them has a story, it turns out. Condensed matter physics wasn't physics until all the money flowed in after the transistor. That's kind of the barbarians knocking down the gate. Atomic physics had, of course, a near-death experience until Bose-Einstein condensation. Plasma physics, of course, is always in the future going to be something. And surface physics, which is a field I know a little bit about, it wasn't physics, and then it became physics, and now it's not physics again. And so all you have to do is have a lunch conversation with somebody in this area and say, well, why is it what you do with physics? And then see what they say. So thank you very much, and I'd be happy to take any questions.
Great, thank you so much. And the fascinating expansion of the original version that you gave a few months ago. We have a few questions written down. First, we have a question by Mark Elowitz. Question is, does this Rowland have anything to do with inventing the Rowland spectrometer configuration?
Oh, Rowland.
Rowland.
Well, I mean, Rowland, of course, was the person who perfected grading spectrometers, for doing spectroscopy. And so, he was a very world famous physicist, one of the ones around in the United States at Johns Hopkins who was known around the world. So that's what he did. And in fact, that picture of him, he's holding in his hand oops, oh, sorry. Let me get back there. He's holding in his hand, right there, a spectrum. So yeah, I mean, that's what I can tell you about Rowland.
Great. Then we have a question from Colin Sayers. He writes, Johns Hopfield 2024 Nobel Prize in Physics is quoted in a recent article saying, physics is not what you're working on, but how you're working on it. Would you agree with this?
Yes. So this has to do with that physics is a way of thought. It's how you approach a problem. And so, for example, that's when I said that when Schrodinger, in What is Life, took the physicist approach, unlike the biological approach, and said, we're not just sort of collecting information and saying, well, this is evolution or this is natural selection. He says, can we actually understand from the point of view of basic physics principles why various things work? So that's already sort of a physics attitude. The other one, which is, I would say, certainly very popular now, is model making. Physicists are comfortable with mathematics. They're comfortable taking a complicated system and trying to make a relatively simple mathematical model, working out its consequences and seeing if you capture the main idea, and not worrying about the fact that this or that, quote, detail doesn't really fit in. And in the biological physics area, you can read, starting 50, 60 years ago, biologists writing articles saying, do we need the physicists? Or is there any place for physics in biology? And there's a lot of hand-wringing associated with this because biologists tend to be interested in some of the details that a physicist might tend to throw out. And then the question is anything the physicist doing of any value to understanding the biological question. Will the biologists, do they even care? And that's a very interesting question, which varies over time as to what is the purpose of biological physics? Is it to be useful to biology? Or, as some will tell you today, is it searching for big principles which govern biological phenomena, or is it something in between? And so there's no doubt that there's a thinking like a physicist, and that just the question is, as you apply it to different areas, is it valuable or not, or do you care or not? And these are questions which are debated to this moment.
Great. Thank you. We have a comment and a question from Cheryl Spencer. She mentions the FIAP is the third largest forum in APS by number of members, many more than FHHP. And she also asks, is cosmology also done in astronomy departments currently? We might add, to what extent?
Yes. Yes. I mean, right. The forum on industrial and applied physics is, of course, alive and well. There's no doubt about that. There is the story of they had this magazine, The Industrial Physicist, which was really sort of a nice magazine, which they just couldn't continue it because they were supposed to be self-supporting through ads, and they weren't able to quite sustain that. But it remains the case, given its size, that the fraction of the membership of the APS of folks who identify as working in industry, it remains quite small. And it's nothing near the 25% that it was in 1920. And as that strategic plan showed, the APS is still trying to figure out ways to make the society of more value to industrial physicists. That I think is that part. And the answer is yes. Cosmology is absolutely done in astronomy departments. In fact, I was visiting the University of Texas, and I was told a story about how there are cosmologists in their physics department and cosmologists in their astronomy department, and they don't even talk to each other. So, and the way they think about things is completely different. And again, that think about things is sort of part of the point. I think your training, whether it be as a physicist or a chemist or an astronomer, there's sort of a culture and a way of thinking that you learn along with the technical details, and that molds how you think about any particular problem. And so a cosmologist in an astronomy department and a cosmologist in a physics department, and the way it's described to me, could be working on exactly the same thing, but their attitude and their approach and even their goals are quite different.
Great, thank you. Next, we have a couple of questions from Vasudevan Lakshminarayanan. First one is, would you consider this year's Nobel Physics Prize winner, shouldn't it really be computer science instead of physics? And secondly, thank you for the talk. Could you please expand upon the peak in biophysics just after World War II?
Yeah. Okay, so this year's Nobel Prizes, I mean, it's absolutely fascinating. It's grist from my mill, because there's all kinds of chatter on social media about what was this prize? Was this a physics prize or what was it? I mean, the Nobel Committee, if you read what they said, it's really a prize for AI, and the chemistry prize is also in that area, but there is no Nobel Prize for AI. So they couldn't give a prize for AI, but happily, the ideas which eventually led through the other person who won the prize to the large language models and such things, they do trace back to the neural nets and the structure of them, which was discussed by Hopfield. Now, Hopfield, his paper was not about computers or anything or machine learning. It was about mammalian brains and such things. And it's a whole question of what impact Hopfield's work has had on actual human learning. But the prize was not for that. It was for machine learning, and they're explicit about that. But happily for the Nobel Committee, it traces back to Hopfield, who, is trained as a physicist. And so therefore it was easy to give half the prize to him and then half for someone who then took it out of human learning and applied it to machine learning. And so, to me, they made it a physics prize because there was an easy route for them to do so. But they're pretty clear that what they were rewarding is AI and ML, and not a giant breakthrough in how the human brain works. That's my feeling about that. Let's see. The second part of the question was about the
Yeah,
peak.
the second question was by,
After
I
World War
thought it
II.
was by the same writer. It's actually by Sarthak Gupta. Could you
Ah,
expand a bit upon the peak in biophysics
yeah, right,
after
right.
World War II?
Right. There's this little tiny, let me see, let's see if I can get there real fast. Uh, yes, there's a rather small peak, and of course it's small. Don't forget, there's an exponential increase in the number of scientists and the number of physicists, period. So I talked about this big one here. This one here is basically a Sputnik related thing. It's this little guy here, which is right after the war. And
We
what
can't
that,
see it right now.
oh,
Somehow
oh, it
check.
didn't, it's not sharing?
Well, I see the main screen that says that's not physics, but I don't actually see the chart that you're
Oh,
discussing. See if
um,
there's anything you can do. Maybe
let me
maybe by
see.
clicking share again, it
Yeah,
will.
let me stop the share and start it again. I'm sorry.
Yeah.
Maybe that's what happened. Share again. And what if we do this? Better?
Yeah, there it is.
Okay. So I talked about this big peak here in 2000. This, so this is the Papa peak, and this is the Mama peak, and the Mama peak is Sputnik. And then there's the baby bear peak down here, which is right after the war. Okay. That has to do with the fact that there were a fair number of people who were disgusted by the use of atomic energy to kill people with the bomb. And there were a number of people who, and again, the total numbers are not large, but it amounts to a net increase in that there are people who left nuclear physics in particular and got into less biological physics than I would say medical physics, which is an interesting topic on its own, wanting to understand better the biological effects of this radiation. And then there were definitely people who just said, who were coming out of graduate school or and deciding what they wanted to get into, and they just said, again, I'm disgusted with the fact that physics, conventional physics, seems to have been co-opted by the military, and I'm going to pick something which probably doesn't have any military implications. I might say just recently I've been looking at folks who were getting their PhDs around or getting started around 1970, and this is when the Vietnam War is raging. And I hear similar things of people who were trying to pick fields that they felt did not have any military applications.
Great. We have a couple of follow-up questions that touch on the topic of AI, which you already went into. I'll just read them out. One by Ilki Kim. AI became a huge issue these days. Nobel Prize in Physics. Is AI physics or will it be? In what sense? Similarly, the next writer comments, what do you think about the future of AI and physics? So basically, do you think AI is evolving towards a spot in physics departments?
Well, I mean, there's already, if I'm not mistaken, is it a forum on machine learning at the APS? And so I mean, it already is a big thing. At my own department here, as at Georgia Tech, advertised for an ML physicist, there was a debate inside the department about what does that mean? Um, it started out by the people promoting it that it's the physics of machine learning. And it was, when pressed, it was a little hard for them to articulate exactly what that meant. And so it relaxed down to somebody who is working in a conventional area, but making heavy use of machine learning. So I'll bet there are people on this call who can tell me what the physics of machine learning. I can't. Um, there's a lot of things like this. Econophysics, for example, is a field, and even urban physics has to do with looking at cities and their problems using the methods of physics. So network physics is another area, where you apply typically statistical methods, of physics, which are very common to and understood by physicists, to problems where they had not been used before. And so, some of these, I'm not sure what type of traction they have gained. Typically, there's a few institutions that decide to take the plunge, and either they bet right or they bet wrong, and it takes a while to figure that out. But I'm not prepared to speculate what the future of the physics of machine learning is.
Great. Before I read out Brad Marston's question, I want to pose a related one so that you answer them together that I had during your talk, which is we look at any of the 3 case studies that you did, for example, the one on acoustics, and we have in the 1940s the acoustic people being shoved out of the Harvard physics department into this engineering sciences and applied physics unit.
Right.
So I'm wondering, of course, we want to get away from stories that talk about institutions doing things. We'd like to know who exactly decided that and why. So part of my question, which hopefully relates to the next one I'm about to read, is do you know who in Harvard made that decision and why? Similarly, Brad Marston writes the following. Could you speak about how the availability of research funding affects what is considered to be physics? For instance, could the infusion of funding into particle physics following World War II have caused other areas, such as acoustics or fluid dynamics, to be pushed out?
Uh, Thank you, Brad. No, I do not know exactly who, if this was a single person's decision or some nameless, faceless committee at Harvard. So, but something, I'm certain one could find it, in the papers at Harvard. In fact, I'm certain of it. I have not done that, so I don't know
Yeah.
whose decision that was. The funding thing, yes, funding in fact drives everything. And so, when I talk about this is in fact, David Kaiser wrote an interesting paper called having to do with boom and bust cycles in physics, and those peaks, which I showed, if you see similar peaks in PhD production, for example, in physics, and it's all related to money. And so after Sputnik, huge amounts of money, went in because we had to catch up with the Russians, and in fact the same thing happened, later with Star Wars and Reagan. Again, we had to catch up, and the money went pouring into physics again. Now, it isn't always stated exactly what it's supposed to be used for, and I would certainly recall in the Star Wars era, which is more, my lifetime, that no matter what area of physics people were in, they tried to figure out a Star Wars angle so they could get their hands on the money. And then they would always say, well, I'm not going to really do any of that stuff. By the time they figure out it's not Star Wars, it'll be too late. I mean, that's how they justify it to themselves. And so great many things are driven by money. Now, the interesting question Brad poses is, did that actually push out money that might have gone for something else? So the only example I can think of that bears on that has to do with the superconducting super collider. And one of the arguments, which was made by people like Phil Anderson, who opposed that machine, was exactly that. The claim was that if you built this thing and then you had to maintain it, that because the science pie is only so big, that would perforce force a reduction in the amount of money going into other things. Well, I mean, in the end, that argument wasn't the one that won the day for killing the SSC. And I think we'd have to really dig deep into, how the budgets for places like the NSF and DOE, how they redistributed things. I can't answer that. What I can say is that when something like when Bill Clinton doubled the NIH budget overnight, which he effectively did, that gave a huge boost to biological things because it was earmarked for that. So I don't think I certainly can't, based on my research, give you a direct answer, but I think it's something one could learn by looking pretty closely at year by year at the budgets of the various agencies.
All right. Next question is from another anonymous writer who writes, as a budding biological physicist trained in physics department, what can I do to be accepted in physics departments in the US where there is no biological physics yet?
uh, well, let's see. If you're applying to a place where they have none, I, I think I would ask them why they're interviewing you, given their history. Um, yeah, let's see.
And more generally, it might be what can make the semi-non-physics seem appealing to the physicists who will make the decision. Say, yeah, we'll bring you in.
yeah, I mean, there's no doubt that hopefully what the type of work you're doing is something where your training as a physicist really sets you apart from other people who might be looking at a related problem, right? And so have you chosen and can you work on something, say, that you can build a model, whether it be an analytic model or a simulation model or something, which you can then compare pretty quantitatively with experiment, right? I mean, that's what we do as physicists. And if you somehow can't do that, then I think it raises the question of whether that's really physics. But if the analog might be condensed matter physics, right? In which you're using the methods of, at least in the early days, you're using the methods of physics to look at this sort of class of issues. And can you make that back and forth between theory and experiment, not necessarily doing it yourself? The other thing, but the biological thing is fascinating because, what is a living thing, right? This gets debated. How do you even define when something is alive? And the physics of life, which, by the way, is the title of the most recent decadal report on biological physics. I would take a look at that, by the way. So again, National Academy of Sciences, you go to their website, and for free, you can download, I think it's 2022. It's called The Physics of Life. The main editor was Bill Bialik at Princeton. And that volume alone will give you a very good sense of how I would say you might want to pitch what you are doing.
Great, great. Next, we have a comment, kind of a compliment to what you mentioned about Freeman Dyson, 1958, writing that cosmology is not a respectable subject.
Right.
Penzler adds an anecdote 50 years ago when, as a graduate student in physics at Princeton, Freeman Dyson gave a colloquium on adaptive optics, a topic which, considering his history, surprised some people. His reply, interesting problems are where you find them.
Yes. Yeah. Yes. And I think this is exactly why you find physicists, this caricature of us, right? Where we think we can do anything. I think what it is that there's an interesting problem somewhere, and I see somewhere in my background, a way in, and maybe I can be useful. The example that I like is the very right before he was tapped to be the director of Los Alamos, Robert Oppenheimer, a fellow who had taken an elementary quantum mechanics course with him, who was a biologist working on photosynthesis, came and showed him some data that he had taken, and asked if Oppenheimer had any ideas. And he thought about it for a bit, and he said, this sounds a lot like internal conversion in nuclei, and wrote down a little theory of it. Oppenheimer just published an abstract in an APS meeting talk, and did nothing. And then years later, it all got written up. And if you look in his list of publications, the very last scientific article that Oppenheimer published in collaboration with this biologist was a complete theory of this energy transfer in photosynthesis, which somebody else had published. They didn't publish it, back in whatever it was, 1939. And someone else published it. It's called Forster transfer. But he had it all right. And it was based upon, he saw an analogy with something that he knew well. And I think that happens with a lot of physicists. They see something and say, oh, this is probably just like that. Now, maybe it is, and maybe it isn't. And of course, it may take a lot of work to figure out if it really is or not. But I think that happens quite a bit. And so that leads to a certain amount of dabbling by different folks. Feynman did that, for example. He dabbled in biology
Mhm.
for a while and then got out of it.
All right. The question by Serkan Husnugli, Husnugil, is pretty much one that you already answered. Somebody else wrote it. Could you talk more about the first peak
Uh,
after the war in biophysics hires? Next, we have a question by Leah O'Brien. Major universities have a separate department for astronomy. How many of the astronomy professors would have a joint appointment or courtesy appointment in physics departments? Is there still elitism here?
so I talked about cosmology, and my original idea was to talk about astrophysics. And when I started looking into it, I discovered it was going to be a hopeless quagmire. And that is because how astronomy, which is of course an ancient science, how astronomy evolved into what is today called astrophysics. And in fact, um, early on, when there was discussion to form an American Astronomical Society, the original title of that was Astronomy and Astrophysics, um, in an actual attempt by people like Hale, to show that astronomy, which up until that time was things like, just where the planets are going and things like that, getting into spectroscopy of light that we get from the stars and things which are or more physicsy. And there was a big fight about this, and the name of that society lasted a few years, and then it got changed back to the American Astronomical Society. They booted out the astrophysics. So, so that's all very complicated, with the relationship between astronomy and what was called astrophysics then. In fact, what's called astronomy today is largely what we might call a certain type of astrophysics. And so I, I chose to stay away from that. And so I can't address the question directly about who thinks who is second class. My guess is that they each think the other is, perhaps. And so I stuck with cosmology, which I thought was.
Sure, sure. Thank you. But do you have an impression of in a physics department, how many people there tend to have joint appointments in the astronomy department?
Um, Joint appointments are a tricky thing. Some people state them and some don't. And is it a courtesy appointment, or is it, shall we say, a 25% appointment? I mean,
Yeah.
these
Is
things are
money
hard to
coming from the
find.
other department or is it just a name affiliation?
Right. It's very hard to tell. What I can tell you is that when you take a physics department and bring astrophysics into it, I've had that happen to me twice. Once when I was a graduate student, and and now here. Um, and there's a definite culture difference, between a conventional physics department and even just astrophysics. Forget astronomy. And so, and there's definitely suspicion, I would say, on the part of the conventional physicists as to what, because those folks say things like, well, we don't really need to take all your courses, you
Mhm.
know, things like that. And so, it's real. The cultural differences are absolutely real, and they trickle down to hiring decisions and options for PhD students and all kinds of things like that.
Mhm. All right. We have a question from an anonymous attendee who wrote, how do you look at materials engineering becoming a large part of condensed matter groups, particularly in things such as quantum computing hardware, development, or batteries, etc.?
Yeah, this is a great question. Right, because solid state physics itself started out as Schmutzphysik, and was shunned by physics departments, and then, like I say, the money beat the doors down, and then there's the connection to material science. So what is the difference there? If you're a condensed matter person and you're very interested in the details of certain condensed matter systems. You don't care about universality. You don't care about what is common. You care about what the differences are. And that's what led ultimately to the division of materials physics,
Mhm.
within the APS, to recognize that there's plenty of folks who feel they're trained and feel in their hearts that they're physicists, but they happen to be working on the same class of problems that material scientists are. Hopefully it's not, heat 'em and beat 'em metallurgy. But that's a fine line. If you go to the Materials Research Society meeting, for example, there's plenty of physicists there. There's plenty of metallurgists there, and they might be working on the same thing. So these boundary issues, they don't matter, of course, from the point of view of the pure science. They don't matter at all, but they do matter for things like jobs and tenure and graduate students and things like that. And so we can't get away from the sociology, which is my motivation for the whole project I'm working on. But it absolutely applies to that boundary as it does to others.
Excellent. We have 3 more questions. The first is anonymous. Is there a case that quantum metrology and quantum information have become physics after originally being researched more in electrical engineering?
Well, let's see, quantum metrology. I mean, I guess I would think in terms of quantum information, certainly, in the sense that, are you going to be trapping atoms? Are you going to be using, defects in diamonds? Are you going to be using semiconductor qubits? I mean, in that sense, there's a great deal of physics which has to be done in order to realize quantum computing. So, I mean, I don't dispute, I think very few people would, that there's serious physics issues which have to be figured out there. Quantum metrology, if you're speaking about the sorts of things they do at NIST, certainly heavy duty physics to things to make definitions of the kilogram and things like that. And I believe I'm pretty sure I mean, those are physicists who work on those problems, unless the questioner has something else in mind.
Sure. Next to last question, just a few more minutes. We have George Herbert. I would say AI and machine learning are computer engineering topics. They are valuable tools for physicists. So it's a helpful comment. And finally, we have a question by Timothy Olzanski. How does the categorization of a subtopic affect the subfield's curriculum development? More broadly thinking of long-term trends, is it a good thing for these fields to be integrated with physics or not? What should we practice as a field going forward?
Yeah, that's a great question.
Categorization of a subtopic, how does that affect the subfield's curriculum development?
Yeah, I would say it definitely does. Because once you give a name to something, anything, right, the name tends to carry a lot of history and prejudices with it. And so once you do that, and the folks who have studied the birth and death of subfields and disciplines, and what it means to be interdisciplinary, for example, have looked at a lot of these sociological questions. And I don't, off the top of my head, can't think of one where the curriculum was specifically addressed, but I'm certain that they absolutely do. In fact, I was just shown a textbook of quantum mechanics for engineers, for example, because in a lot of engineering disciplines now, they really need to worry seriously about quantum things. And when you look at this textbook, it really doesn't read like, I mean, the way of physics quantum mechanics, the book does it all. And of course, it's not supposed to. And so how that actually gets taught in an engineering department, it'll be very interesting to be, I don't have to be a fly on the wall. I can sit in the back and listen and learn that. But I'm absolutely certain that it does make a difference how you choose. Once quantum mechanics becomes part of engineering, it definitely affects curriculum development, at least over there.
We had 95 participants at one point. We are down to 54. One last question has popped up. I might as well read it. Anonymous. Most of the physics departments don't teach fluid dynamics courses anymore. Do you know when it started happening? Acoustics was, excluded, fluid dynamics. Is that happening?
Yeah.
When did that start?
Yeah. Okay. So first of all, there's of course a division of fluid dynamics in the APS. It's one of the old divisions, in fact, and it's the same sort of thing. It used to be that fluids was a part of every physicist's education. Today, they're a part of no physicist's education, more or less. I haven't looked into that one the way I have acoustics. What I do now, there was a revival of fluids in connection with nonlinear dynamics and chaos, because turbulence, fluid turbulence, that area also got revived amongst physicists because the methods of nonlinear dynamics and such things were helpful for understanding fluids. And so there's plenty of physicists in my own department who go to, fluid dynamics meetings to this day, because, that's the medium where they're interested in looking at nonlinear problems. So fluids, I think, is a slightly different status. It's probably come back into, it's not certainly a required course, but at least a course exists in some physics departments in fluids, where I'm certain they were gone for some years. So that would be an interesting one to track, but I have not done it myself.
Thank you, Andy. Thank you so much. We've been here an hour and a half. I want to thank everyone still with us. In case you're interested, November 1st, we've got a talk by Frances Hellman, A Brief History of Women in APS. And November 4th, we've got the talk by Sarah Bridger, The American Physical Society and Cold War Political Activism. You should, as APS members, have received or will receive emails about these. In any case, thank you all, and let's give a nice round of applause, virtual applause, to Andy Zangwill. Look up his book, Modern Electrodynamics. You won't regret it. Thank you, everyone. Take good care.
Thank you. Bye-bye.
Bye-bye.
Thanks, Alberto. Let's see.